don't really know why everything around us exists, why the universe has form, why objects have mass. The fundamental question about why we're here remains unanswered. But today's announcement could change all of that.
For decades, scientists have been searching for a particle that will give us an insight into the workings of the universe, the Higgs boson. And to find it, they've had to recreate the conditions of the Big Bang.
Billions have been spent in the hunt for the elusive Higgs. To detect it, scientists have built the world's largest particle accelerator, the Large Hadron Collider, an 18-mile tunnel below the French-Swiss border. Subatomic particles called protons are fired in opposite directions through the tunnel at a rate approaching the speed of light. And with the help of magnets, they smash into each other. Detectors monitor the collisions and search the debris for signs of the Higgs boson. But what is the Higgs boson? For the last 2 years, scientists at the CERN nuclear laboratory have been searching their results in the hunt for the Higgs. The theory about its existence has been around for about 50 years. But until now, no one had seen any sign of it. As the universe cooled after the Big Bang, an invisible force known as the Higgs field formed together with its associated Higgs boson particle. The field permeates the entire universe, and when a particle without mass passes through the field, it accumulates mass. It develops form. It's why there's something rather than nothing.
It's very exciting, and it is also very important because physics needs just to be driven by a mixture of good theories, but of solid experimental data. This hunt of the Higgs is like fishing with an ancient way, in which instead of using modern tools, you were removing the water from the pond. And so it might look tedious, but it's the only very clean way at the end of the day, when you have removed all the water from the pond, just to find even the smallest fish.
And in the run-up to today's announcement, there was a real buzz, a sense that we were on the verge of something big.
I would say it will be a milestone in this particular field, whatever the results will be.
So we took data now for 2 years, and I was pretty much involved in data taking. And so of course it's with big excitement.
In the control room at CERN, they're testing the collider's capabilities.
Wow, nice loss map.
When the particle physicists aren't using this machine, it's time for the engineers to see how far they can really push it to its limits.
Harnessing the power of this super collider is a tremendous technical feat, and the excitement is palpable.
It's become, in some sense, a holy grail quest. A large part of the motivation for the Large Hadron Collider was to find this Higgs boson, or whatever replaces it. So this really is a culminating point.
The Higgs boson is part of what is known as the standard model of physics. This is an instruction booklet for how the cosmos works, a framework that explains how the different particles and forces interact. Professor John Ellis is a former head of theoretical physics at CERN and expert in spotting particles amongst the collider's debris.
The standard model that describes all of fundamental particle physics. You can think of it as being an enormous, great big jigsaw puzzle, but there is a piece missing right in the middle there. And we've been looking for it for over 30 years now, and finally, maybe hidden under the back of the LHC sofa, we're finally finding it.
Without the Higgs, the standard model is incomplete. Finding it would help confirm everything we know about modern physics, built layer upon layer since 1900.
But then in September, something happened that could blow all of this apart.
An nearly a century, scientists have thought that nothing can travel faster than the speed of light.
The neutrinos are arriving sooner than they should.
Something going faster than light is just not allowed. This speed of light is not an arbitrary speed limit that we made up because we like it. It's built into our understanding of the very space and time around us. It's the very stage on which physics happens.
What so rocked the world of physics was a beam of neutrinos, the most common and the most weird of all fundamental particles. They'd been sent 450 miles from CERN to a laboratory underground deep inside a mountain called Gran Sasso in Italy. But they'd arrived 60 billionths of a second sooner than light would have done travelling the same distance. Some scientists thought CERN had sent the neutrinos in bunches too wide to monitor accurately, so they did it again, but with a narrower beam.
So we sent beam for 2 nanoseconds to the target, produce neutrinos, and they measure it in Italy. So of course you have a very precise timing measurement on this, and the result was the same as with the measurements they did before with these long beams.
Professor John Butterworth works in one of the two teams searching for the Higgs at CERN. He thinks there are many ways the neutrino experiment could have gone wrong.
Because it's such an out there result. I mean, there are many, many thousands of results that confirm relativity and this one result that violates it. So before you throw away relativity and really change our understanding so much, you really want to be very sure. But in the end, I mean, it's a careful experiment. They've addressed many of the systematics, even ones that people raised initially. I think all there is for it now is we have to, as with any science, you have to repeat the result until you're sure.
Making sense of these results throws up all sorts of possibilities. Some theories talk of 10 dimensions of space. So could the neutrinos have taken a shortcut through another dimension? Arriving in Italy, back in our dimension, sooner than expected.
The result is so revolutionary, it's got to be repeated before it's seen as robust. But even if it is, would it mean anything to all of us in the real world?
I'm sure that if you asked Einstein back in 1905 what real-world applications would his theory of relativity have, he wouldn't have been able to give you an answer. Okay? But now, of course, we know that relativity has to be taken into account in the global positioning system, sat-nav. As for neutrinos travelling faster than the speed of light, this is perhaps a crazy remark. But I noticed that in the financial world, they are now timing their trades at the level of nanoseconds. So if you could make neutrinos go a little bit faster than light, maybe somebody would find a competitive edge.
With each of us facing our daily troubles, and with the world of finance and politics in turmoil all around us, why should it matter whether we find the Higgs, whether neutrinos go faster than the speed of light, if there's some deeper symmetry under the surface, or not?
There is, in my opinion, a very important need for investing a very tiny amount of our wealth in future, in what is called curiosity-driven research. Because without that, we are doomed.
It's been one of the most incredible years for physics. Hints of the Higgs, and then out of nowhere, particles that might just have broken the cosmic speed limit. We could be on the verge of a new physics, a new understanding of our universe, and a new understanding of our place within it.